welcome to working through the lever problems for activity 112. So first I'll show you that I've got a page where I've got my formulas that we're going to be using on these problems. The ideal mechanical advantage is the ratio of the distances. Those distances are the distance of the effort and the distance of the resistance. And with a lever, that distance is the distance along the lever arm from the fulcrum to the point at which the effort force is applied or the resistance force. The actual mechanical advantage is the ratio of the forces, okay, the resistance force and the effort force. The turning effect, or the desire for a lever to rotate and turn, is quantified and called a moment. A moment is the product of the force applied as well as the distance that force was applied from the fulcrum. So how far away is the force and the fulcrum from each other? If you were to apply a force right at the fulcrum, your distance would be 0, and you'd get a 0 moment, and that makes sense. If you push right at the fulcrum, you're not going to create a desire for the lever to turn one way or the other. And then should we have multiple forces working on the lever in opposite rotational directions, we can get into a rotational kind of static equilibrium where the desire to turn clockwise and the desire to turn counterclockwise are matched or balanced. And so that is the case where a moment is equal to another moment. Of course, a moment is a force times the distance. So we can make a substitution that we really have a force times the distance to create one moment, and we have a different force and distance pair to make a different moment, and those moments would then be equal, just in opposite directions rotationally to create that static equilibrium. So these are the formulas that we're going to be using. Question number 1 asked you to simply draw and annotate the picture, and so I've already got that done. And they told us that we had a resistance force of 50 pounds, an effort force of 15 pounds. They told us that it was a first-class lever, which means the fulcrum is somewhere in between those two forces. They also told us that the distance that the effort force was applied to the fulcrum, or to the lever, was 4 feet from the fulcrum. So there's our picture. Alright, number 2, they ask what is the actual mechanical advantage. So actual mechanical advantage, or AMA, is equal to the ratio of the forces, FR over FE. In this problem, we were told that we had 50 pounds of resistance force and 15 pounds of effort force. It's good to note that the units do cancel out, and mechanical advantage does not have a unit. So we end up with 50 over 15. Both of those are divisible by 5. That would be 10 thirds, or 3.3 repeating. That was question number 2. Question number 3 says, using static equilibrium equations, calculate the length from the fulcrum to the resistance force. Okay? So what they did not give us was this distance here. How far along the lever arm was the resistance from the fulcrum? So that distance we're going to call our dr. They said using static equilibrium equations. So that means we're going to assume that 15 and 50, they're telling us, is putting this lever into a state of balance where the desire to turn clockwise and the desire to turn counterclockwise are matched. So we can say that we have a moment. We could use CW and CCW, or here I'm going to use E and R. So a moment created due to the effort, and another moment created due to the resistance. That they're in balance, they're equal. And so the effort moment was created by an effort force, and that effort force was applied some distance from the fulcrum. The moment due to the resistance was created due to a force of resistance, again some distance from the fulcrum. So this static equilibrium relationship they're discussing or telling us to use really involves these four variables. Two different forces, two different distances. Looking at the problem what they give me, I have 3 out of the 4 things. I know my effort force is 15 pounds, and I know that distance from the fulcrum for that 15 pounds was 4 feet. On the resistance side, we knew we had 50 pounds of resistance, but we did not know how far away along the lever arm it was placed. And so we can now use this equation to solve for dr. So 15 times 4 is 60. 60 equals 50 times dr. We will then divide both sides by by 50 to get dr alone. Whatever we do to one side, we do to the other. And so the distance the resistance force was applied was 60 over 50, or 6/5, or that would be 1.2 feet. Okay, since our other distance was in feet, this will be in feet as well, 1.2 feet. And that's a first class lever. Alright, moving on. Okay, so the next problem discusses a wheelbarrow being used to lift 200 pounds. The length from the center of the wheel to the center of the load is 2 feet, and from the length of from the wheel to the effort is 5 feet. So I've already gone ahead and annotated this, kind of in order to try to give some context of maybe a wheelbarrow, very subtly, but in my dark blue I've got a fulcrum. I've got, in essence, a lever arm. I have a load that is placed closer to the wheel. That is, in a wheelbarrow, you're putting the load here close to the wheel. So I've got a force, I don't know what it says to, it should be R, of 200 pounds. And that's 2 feet from the center of the wheel. We have the operator over here holding onto the handle, some 5 feet away. And they didn't tell us how much effort this person has to apply to be able to lift this 200-pound load. But there's number 4, which is just trying to sketch out and annotate my problem. But hopefully you see that I have a lever arm with the fulcrum at one end, the resistance along the lever arm closer to the fulcrum than the effort. And this is called a second-class lever, where the effort is further from the fulcrum than the resistance, yet they're both on the same side of the lever, or of the fulcrum, of the lever arm. Unlike a first-class lever, where they're on opposite sides of the fulcrum. Okay? Let's see what they ask for next. Number 5 says, what is the ideal mechanical advantage of the system? Well, the ideal mechanical advantage of a system is equal to the ratio of the distances. So, because we're only using distances and not the real forces, we're not going to be able to account for friction. So this is giving you kind of the best case scenario. In the real world, right, when you just measure the distances and calculate a mechanical advantage, right, you're not accounting for friction and things that would potentially decrease your mechanical advantage. And so that's why we call it ideal, where if we had actual measurements of forces, we could get the actual. Okay, so this is pretty simple. They've given us the two distances. The effort is being applied at 5 feet from the fulcrum, and the resistance is being applied at 2 feet. So it's just the ratio of 5 to 2, or 2.5. Those were both in feet. We're dividing, so those feet cancel out. There is no unit on mechanical advantage. It's just the number, 2.5. Number 6. Again, asks, kind of like number 3, to use static equilibrium equations, and to use that to figure out the ideal effort force needed to overcome the resistance force. So, using static equilibrium means we're setting the moments equal, one moment due to the effort and one due to the resistance. The effort moment is created by the force, the effort force, and then the distance that force was from the fulcrum. The moment due to the resistance was again based on that resistance force and how far that resistance force was applied from the fulcrum. So we don't have that effort force. That's what we're trying to figure out, is how much is it going to take to overcome that 200 pounds of resistance. We do know that it's 5 feet from the fulcrum, and we we know our 200 pounds of resistance was 2 feet away. So we've plugged in our knowns. We end up with what they asked us to solve for as our only unknown, so we're good to go. And we can just solve. I'm going to simplify the right side to be 400. And then I will show that we're going to divide both sides of the equation by 5. Cancel out that factor of 5. And Fe, the effort force, is 400 divided by 5, which is going to be 80 pounds. Alright, for problems 7, 8, and 9, we're looking at a third class lever, which is a pair of tweezers, and I've gone ahead and annotated what they've given us here, which is a pair of tweezers that are 4 inches long, a technician applying 1 pound of effort force, and to remove a sliver. And the sliver can't experience more than 1/5 of a pound of force, otherwise you'll break it. And so they're telling us that it's going to be, to get that 1/5, it's going to be 1 pound of effort force by the tech to get that. And if they squeeze harder, obviously that would make that go up. So we're going to count those as the values that we've got. Obviously they could squeeze a little less, and they wouldn't experience as much force here, but then maybe it would slide out, or kind of slip off the tweezers. Alright, so that's our story. It's our problem, and they're asking us for what? In number 8. Number 8, they ask for, what is the actual mechanical advantage? Okay, so number 8, AMA, actual mechanical advantage, is simply the ratio of the forces. So the resistance force is the 1/5 of a pound, and the effort is 1. 1/5 is also 0.2, divided by 1 doesn't change anything, so it's really just 0.2. Our units would have been pounds and pounds, they cancel out, so there's no units on mechanical advantage. Number 9, I think like number 3 and number 6, they ask us to use static equilibrium equations. They ask us to do this to figure out how far from the fulcrum the tweezers must be held to avoid damaging the sliver. You see, if the person slides their hands too far along this way, then their 1 pound will create more force. Or if they're too close to the fulcrum, they won't create the needed or required 1/5 pound of force. So we're kind of looking for what is that exact place that they really should place their fingers so that when they apply 1 pound of force, they get this 1/5 pound at the end. So static equilibrium is that rotationally, think this lever arm, okay, look at kind of one side of the tweezer, is wanting to rotate one direction as the technician pushes here, but the sliver is pushing in the opposite direction. So we have a moment due to the effort and a moment due to the resistance. So the effort, we have a force and a distance. In the resistance moment, we have, again, a force and a distance. Okay, on the effort side, it's our 1 pound of force, and we don't know how far from the fulcrum that is. On the sliver side, we don't want more than 1/5 of a pound of force, and we know that it's the full length of the tweezers. One end is the fulcrum, and the other end is where the sliver is, which is 4 inches. Alright, well 1 times dE is simply dE, and multiplying a fifth by 4, we get 4/5, or 0.8 inches, and that is the distance that the tech should place their fingers from the fulcrum. So right here, this should be 0.8 inches, is what we just determined. Okay, they put their fingers any further down, and they actually are going to create a bigger force on this end. They move their fingers too close to the fulcrum, and they won't get the required resistance force. There you go. So that is going to conclude kind of working through the lever problems. I'm going to separate videos for each simple machine from this activity. So if you needed help with a different simple machine, just look for the other links. Hope this helped.